Good afternoon. So welcome to Magdalen College and to the Grove Auditorium for our Calleva Seminar this afternoon. My name is Rob Gilbert and I'm serving as Director of the Calleva Centre, which is a research centre based here at Magdalen, which was founded over a decade ago now from the generous gift of Stephen and Caroline Butt. And since then has run a series of research projects. In the last couple of years it's been refounded and kind of refocused on a number of key questions around risk for the first sort of set of new awards that we've been making. This is the second seminar in a series that has started from that refoundation of the centre. Last term we had, or the term before, sorry, we had one from Tim Barraclough on his work for a newly funded Calleva project, looking at genetic analysis and how that can be used to improve crop sustainability using knowledge of evolution. And today we've got something which is sort of related, also about how we address human risk, from Jenny Castle and her team, talking, as you can see, about climate change effects and solutions with a team that's partly funded from the Calleva Centre, again, from this point going forward for at least a couple of years. So thanks to Jenny for being here today with her colleagues to present, and then a special thanks to Hampton Gaddy, who's our graduate administrative assistant for the Calleva Centre, who's been really important in getting the programme that we've got now running up, and especially for today in setting up today's event. So thanks to Hampton very much indeed. I hope you enjoy the event. I'm going to hand over to Jenny now, and then at the end, of course, there'll be a chance for questions, and Jenny and her team will look after that with you. So thanks again.
Hello, thank you very much for coming along today. It's a great pleasure to meet you all. Ooh, this sounds very loud. Am I booming away? It's okay, good. Let me thank the Calleva Centre in particular and Rob and Hampton for inviting us to give this seminar. No one wants to hear me talk for a long period of time, so fortunately you don't have to, because I've got a fantastic team here that are going to present as well. So I'm going to give you a bit of an idea of the topic, and then you'll hear a bit more about the kind of research that we're planning to do. So, as I say, thanks very much to the generous support of the Calleva Centre. We're launching our new project. It's going to launch in October this year, and it's climate change as a dangerous threat to human welfare. And so the aim of this seminar is really to give you a sense of what we're going to be aiming to do in this project. But let's start with some data. Okay, if in doubt, look at the data. So this, I think, is a really interesting plot. This plot shows the change in atmospheric CO2 going back 800,000 years ago. So each of these is 1,000-year intervals. So we're looking back in time. This all comes from ice core data, and we measure the atmospheric CO2 in the atmosphere. And you can see there's been some huge variations over this really long time series. Now, 1 part per million is 7,800 kilograms of CO2, right? That's a huge amount. And look at the variation here. So really interesting data, but this is what's happened over the last 250 years. This spike here is carbon dioxide emissions since the Industrial Revolution. This is the human aspect of climate change. And that's why it's really fundamental for us to be working on this. Just look at that size of that shift. More than 130 parts per million in less than 250 years. And 1 part per million was worth 7,800 kilograms. So it's really astonishing. So it's really crucial to address this question. So we're going to look at the past, and we can draw some understanding from past mass extinctions from life on Earth. And it's clear that the Earth has undergone many different changes. There's been a huge amount of change, but the climate change has really been the main culprit that's driven mass extinctions. Now, those mass extinctions haven't been human-induced, but it's due to changes in climate. And humanity now is just the latest trigger in the climate change-induced possibility of mass extinctions. So there's a lot of compelling approaches and evidence from many disciplines. There's increasing not just CO2, but atmospheric greenhouse gases, leading to worldwide temperatures slowly increasing on a varying trend. And when I say slowly increasing, maybe that's the wrong word. Actually, they're much more rapidly increasing than we had anticipated. But economic analysis can offer some ideas. The key problem is that the distributions shift. You just saw from that data that immense spike, and that's because distributions are shifting, but we can undertake action. But it is really urgent, and that motivates our project. So the route map, I'll start by talking, but I'll try and keep it short. I'll give you an argument about why climate change really is the global threat to humanity and what we should do about it. And then the team are going to talk about some of the research that you can do under this umbrella of climate change and economics combined. So Jonas will start looking at the way to net zero. Then Xiyu, Jiao will talk about econometric methods for evaluating climate policy. Menghan and Yuan will talk about climate change modeling and predicting economic impacts. And then Susana Martins will talk about the financial risks involved in climate. So here's another graph that I think is quite stark. This is basically looking at extinctions from past fossil records. So you can see that at the end of each era, we get a high point of the mass extinction. So on the bottom axis, we've got the millions of years before the present time. On the vertical axis, we've got the proportion of extinction occurrences. And these 5 dots are really pointing out some key mass extinction events. All of these are actually due to a changing climate. So climate change really is fundamental here. The first is due to probably global cooling. The second, again, likely to be cooling. The third, this was the really big one. If I go back to that graph, look at the third, that's 50% of extinction occurrences, really dramatic there. And that's essentially prolonged volcanic eruptions from the Siberian traps extinguish a huge amount. The fourth, again, from Triassic period, and the fifth at the boundary there. All of these, as I say, are due to climate change, cooling or heating. Okay? So it's not the climate that matters, it's climate change. Change being the absolutely fundamental word. And it's that humanity is changing the climate, and the Earth cannot adapt rapidly enough. It's the speed of change that's really problematic. Here's another example. These are recent extinction rates. So we've got on the bottom axis here, pre-human, recent, in other words, post-1500, and these are predictions for near future extinctions. And on the vertical axis, we've got the extinction rate, but notice this is not linear. This is exponentially increasing, okay? And so the estimated extinction rates are really accelerating very rapidly due to human behavior. So our planet's climate depends on the energy balance between the sun's incoming radiation and then re-radiation from that. And the atmospheric greenhouse gases, like water vapor and carbon dioxide, are really crucial in retaining the heat of the Earth. If it's too depleted, it means the planet cools. And in fact, we've had periods in which there's glaciation in Death Valley. Whereas too much greenhouse gases leads to very warm periods. An example of that about 50 million years ago. So past climate change is driven by natural forces. Clearly, before humans were around, all of this was due to natural forces, mostly plate tectonics, volcanism, orbital variations, and life has survived these changes. And they've actually thrived in very different global temperatures. But, as I've just shown you, en route, many of these species went extinct, even if long after new species come around. And as I say, change is that key word, and the more rapid change occurs, the less adaptive we can be. So let me show you what the costs of this climate change are. The unintended cost of industrial revolution. So UK was essentially started the Industrial Revolution, and since then we've been pumping out carbon dioxide, and this is the annual change in carbon dioxide from 1960 just up to 2020. Look at it, increasing, and this is despite all the COPs that we've met to try and reduce carbon dioxide emissions. So they're still rapidly increasing. This is the impact of that carbon dioxide emissions. This is the global mean surface temperature deviations. In other words, how hot is our Earth becoming? This is going back to about 1860 up to present day, and we've got the Arctic temperature in red and the global temperature in blue, and you can see since the 50s and 60s, we've got increasing global temperatures. The Arctic temperatures are actually increasing much more rapidly, and think about that with ice melt, etc. Then we've got ocean heat content. So in other words, our oceans are also warming, and they're warming really rapidly. This is the degree of ocean warming, and of course, the more oceans warm, the more it expands, the more risk we have of flooding and things. And finally, sea level forecasts. This goes from 1880 up to 2020, so you can see the actual sea level is red. It's actually an accelerating trend. So sea level rise is increasing. If you were to extrapolate forward from, say, the 20s, you can see you'd be down here. I say down, you'd be up here. But actually, sea level rise is rapidly increasing over this period. All of these are consequences of this increase in global carbon dioxide emissions, and indeed global greenhouse gas emissions. So how much of it is our fault, and how much of it is just the natural forces in the world? So the red line is actually the carbon dioxide emissions from a volcano in Hawaii, Mauna Loa. And they've got one of the longest records of continuous measurements for carbon dioxide that we have in the world. Now, the main natural causes of carbon dioxide emissions are essentially vegetation. So trees grow and they absorb carbon dioxide and then they die back and release. And this is the vegetation index that measures that essentially seasonal pattern of vegetation. The other one is a southern oscillation index. So this is El Nino and La Nina, which is essentially the degree of pressure in the southern oceans. What's left? That's what humans do in terms of emitting carbon dioxide. And that is the blue dashed line here. So essentially, almost everything is due to human behavior. So we need to change human behavior, basically. Just to show you what the distributions look like. So this is the distribution of global atmospheric CO2, and this is from 1957 to 72. And if we move forward a period, up to 72 to 87, you can see the distribution has shifted upwards. In other words, we're essentially pumping out much more carbon dioxide the following decades. If we go forward again, another shift, and if we go forward to the present time, this is after COPs, just look how the distribution has shifted so far out here. We're pumping out many more emissions in terms of carbon dioxide than we had previously. And that's due to energy generation, artificial fertilizers, deforestation, animal husbandry, farming, construction, waste. All of these need to be addressed. So I hope I've motivated why this project is important. Okay, so let me introduce what we're going to do. This is the project. So the project is about the path to net zero. We want to look at evidence-based policy. It needs to be meticulous, accurate, and statistically sound. And as I've said, the climate of the planet Earth depends on the energy balance. But the greenhouse gas emissions are due to human behavior and economic activity. So let's use those models that we use to model human behavior and their economic activity and apply them to modeling climate change outcomes and implications. So this is our project. We're going to use statistical methodology for analyzing climate and economic data. We're going to research policies that aim to get us to net zero. We're going to evaluate whether those policies are effective at both the local, national, and international scale. And we also hope to contribute to Magdalen College's sustainability policy. So you'll see some of these examples in the team's presentations in a minute. So this is the team. So as I say, I'm the project lead for the Calleva project. Jonas, who's going to talk in a minute, has just been appointed as one of the new postdocs in econometrics with Magdalen. Another new postdoc, Jiao, she should be online, I think, so she's currently finishing her PhD at the Max Planck Institute, and she's a climate scientist, and she'll be joining Magdalen as postdoc. And then we have a new PhD student, Ebba Mark, who's going to be doing a PhD in geography here at Magdalen as well. So all of these posts are generously funded by Calleva to work on this project. Then we have other members of the team that are contributing to the overall objectives of the policy. And these three here, you're all going to hear from in a minute: Menghan, Xiyu, and Susana. And then we've got a much broader team who are all contributing to the broad questions in the project as well. So given the number of us working in this, we hope we can get some really interesting output. So what are the questions we're going to be asking in this research project? Well, we have three parallel and interwoven strands of research. We're going to be looking at forecasting climate and economic outcomes when the world is rapidly changing. We're going to look at how best to design climate mitigation policies, and we're going to ensure a just transition. And the argument for looking at all of these jointly is that we need really good predictions of the implications of climate change, that's our first strand, to enable us to design climate mitigation policies, which is the second strand, which, in order for these mitigation policies to be successful, must hinge on ensuring wide public support, which means we have to have a just transition to net zero, leading to a clear path to net zero greenhouse gas emissions. And the methodology we're going to use to apply to this project is we're going to explain the empirical evidence, but take account of human behavior, because it's all driven by human behavior. That human behavior, unfortunately, is very unpredictable, and it's ever-changing, so we're going to have to try and find a close approximation to how human behavior changes and evolves over time. It requires us to allow for many explanatory variables, loads of dynamic reactions, outliers, shifts, non-linearities. Everything under the sun is going to be in here. But we've got powerful tools embodied in econometric software to try and help address these issues. So what are the outcomes that we're hoping to achieve from this project? Well, we want more robust climate models based on cutting-edge econometric methods with a focus on policy-relevant topics. We want to link the empirical feedbacks between greenhouse gas emissions and socio-economic processes. We've got a clear argument here, given the broad range in the team, of knowledge exchange between the climate scientists and the social scientists, and that should aim to bridge the gap by showing commonalities and differences between the physical and the statistical approaches. At the moment, you'd be amazed at how separate these two different research strands are. The climate scientists in doing physical modeling in one hand and the statisticians doing the statistical modeling in another. So that's going to be a really important aspect. New research showing how net zero can be achieved in a fair and equitable way. So we want to look at proposing policies to focus on stranded workers and their families, not just stranded assets, which is a big field. Issues of poverty as well. And also support Magdalen College in its progress towards its net zero claims, objectives of 50% reduction in carbon emissions by 2030 and net zero by 2050. So there are key outcomes. So I guess here I'll just take a pause because I've kind of set up the project, and then the team are going to talk about some very specific aspects of research. So I thought I'd talk a bit about the kind of research that I'm interested in doing, and to use an ancient framework of earth, air, fire, and water. These are the essential ingredients for life. So let's explore how they affect climate change and the actions humanity can take to avoid disaster. So in terms of Earth, 10% of land is covered by glaciers. I thought that was a surprising number. 19% is barren, and the remainder is habitable, and that needs to house 8 billion people. The satellite images suggest that only less than 6% of the UK's land is built on, and another 3% is green urban. Globally, that's closer to 1%. The global food supply uses roughly 40% of the planet's habitable land, 50 million kilometers squared, and forests have a similar share, but unfortunately are falling. The energy production and manufacturing using coal, oil, and natural gas, transport, mainly oil, construction, essentially, especially cement and concrete, and agriculture worldwide presently combine to release about 4 parts per million of greenhouse gases per annum. Remember, that was 7,800 billion kilograms of CO2 per part per million. That's a lot. Crops grown using artificial fertilizers based on fossil fuels release nitrous oxide, really dangerous greenhouse gas. Even more dangerous is methane from animal husbandry and rice cultivation, although it does die out more rapidly. And deforestation, of course, releases CO2. The issue here, all of these arguments, is that warming begets warming. So the more warming we have, the more warming we're inducing. And here's some examples of the implications of that. As we warm, we get more extreme events. So we get more hurricanes, these are dust storms, wildfires, flooding, and tropical storm events. So these really matter. What about the second category, air? Well, air you can think of as a placeholder for our atmosphere. And our atmosphere is mostly nitrogen with oxygen and greenhouse gases. But our atmosphere is really thin. It's a thin blue line around the planet, as thick as a sheet of paper around a soccer ball. Really thin. And the problem with that is, of course, it's easy to see how we can alter its greenhouse gas properties. What about fire? Fire is the placeholder for energy, and that's presently energy mostly obtained from burning fossil fuels, releasing greenhouse gases in vast volumes. And you've seen data like this before. This is the data I showed you looking at the past 800,000 years before the present, and this is the CO2 emissions from the Mauna Loa measurement in Hawaii. And you can see just how significant they are. They're still accelerating despite all the COPs that we've had. And finally, water. The Earth is a big blue sphere. You think of Earth as majority water-based. And so the oceans look vast, but actually they're very shallow. And all the water is just a big puddle. So this graph really shows very neatly this first sphere, number one, is all the water on the planet. Okay? That sphere is only 860 miles in diameter. Then the second sphere, this tiny sphere here, is just the fresh liquid water, just 169.5 miles in diameter. Freshwater lakes and rivers, I'm not sure you can even see the dot. See the dot, tiny dot just below the smaller dot there. That's 34.9 diameters in diameter. So we actually have very little water on our planet. That means it's easy to heat it, pollute it, fill it with plastic waste, and turn it to weak carbonic acid. So that's all a pretty negative message, isn't it? I hope you're not all feeling a bit depressed. All is not lost. Humanity caused this problem, but they can do something about it. So here's a graph of CO2 emissions per capita for the UK. So far you've seen global data on CO2 emissions. This is for the UK from 1860 up to the present day. UK CO2 emissions rose very dramatically up to the First World War. We have a lot of volatility in the interwar period, but then from the 1970s, it's been falling rapidly, and the fall has been accelerating. Okay? So we're currently emitting less CO2 per capita than before 1860, and yet real incomes have risen sevenfold over this period. So we can reduce carbon dioxide emissions without it costing us heavily. This shows how the composition of energy has changed over time. So the sort of purpley line here, which goes up here and then comes down, is coal. So you can see coal rose dramatically, and in fact almost all total fuel was coal until the early 20s, and then it's been gradually declining. The dashed blue line is oil, and that really took off as coal started to fall. Then the lighter green line is natural gas, but you can see even that's starting to fall. And the really interesting one is wind, solar, and hydro, which is suddenly taking off from 2000. And the costs of renewable energy have fallen dramatically over this period. So as these accelerate, costs of replacing brown energy with green energy really has changed. Another interesting fact is how much more efficient we are. This is the ratio of CO2 emissions to capital stock for the UK over this long time period. In other words, how much emissions that we have relative to the amount of capital that we have in the economy. This has fallen by 92%. Okay? We're getting much more efficient in terms of our production. And if this continues, then you can see actually we need much less CO2, or indeed much less energy to produce the kind of capital that we need. And finally, for any American in there, the British are doing much better than the Americans on this front. This is the same plot of CO2 emissions per capita for the US relative and this is the UK. So for the US, they're up at about, 16, 17 tons per capita, and the UK actually never even reached in their worst moments those kind of emissions per capita. So we're down at about 5.5 now, whereas the US up at about 16, so a huge difference there. So, having invented the Industrial Revolution, transforming the world's wealth that came at the cost of climate change, but the UK is now one of the first out in the sense that they've reduced carbon dioxide emissions below the level first reached in 1894. UK's 33% emissions reductions since 2008 are impressive given the large increase globally. So if you look at the global data, it just keeps on accelerating. So climate policy can be effective. We've seen big reductions in CO2 emissions, and to do so, we need to do so by eliminating coal, improving the capital stock, and increasing renewables. So large emissions reductions haven't involved major aggregate costs, but the local losses haven't been tackled. And they really need to be addressed, because in order for a transition to a green economy, stranded people mustn't be abandoned. So I've got the last couple of slides, which is the kind of research that I'm working on at the moment, which is thinking about what we call sensitive intervention points. That's a point where a very small change can actually trigger a much bigger change. And you can think about these as levering policy actions and technology development. So here's our argument for 5 sensitive intervention points to get to net zero by 2050. So you need to vastly expand non-greenhouse gas electricity. In other words, no coal, much less CO2. Decarbonize ground transport, ensure no oil, and store the electricity in a vehicle-to-grid system. Decarbonize households and construction, then that gives you no natural gas. Decarbonize industry, which means less of all fossil fuels, and then reduce the agricultural greenhouse gas footprint, so that gives you less carbon dioxide, nitrous oxide, and methane. So there is hope for the future from the renewable energy in terms of earth, thermal and bio, air, wind energy, fire, solar and nuclear, and water, hydro, tides, and waves. And that basically summarizes the argument there. So I think I've talked long enough. You've probably heard far too much from me. So let me hand over to Jonas, who will tell you something about the kind of research we can do to contribute to the project.
Okay, thank you, Jenny. Can you all hear me all right? Perfect, good. Thanks all for coming, and thanks for the interest in the project. I want to give you a quick overview over 3 different projects, which have very different research questions and methodologies, but they are all related to net zero. How can we get there, or are we on the way already? The first project is about fiscal spending, and this was actually a project with the World Bank. And in this project, we analyzed the fiscal spending of 85 countries in response to the COVID-19 crisis. And at the time of writing, like mid-2021, the database that we used had recorded a total of $20 trillion of fiscal policies. So that's a huge amount. And most of that spending was actually for rescue spending. So things like the furlough scheme, helping struggling business, and so on. So there's really not that much scope for strategic investments. But 15% of these 20 trillion were actually used for long-term recovery spending. So that's really spending to stimulate growth in the long run and help the economy recover. So here's much more scope for strategic decisions. And we relied on the literature to, in a first step, categorize all these different policies into policy archetypes, of which we had about 160. And then again, relying on the literature, relied on expert judgments on whether these archetypes are likely to increase greenhouse gas emissions in the long term, in which case we classified them as brown, decrease them, then they would be classified as green, or if they would stay roughly constant or have cancelling effects, and then they would be classified as neutral. And then in our final result, we found that the share of recovery spending that can be classified as green and therefore is likely to reduce greenhouse gas emissions in the long term is 20%. So that's really nice. But unfortunately, we also found that an equal share of recovery spending was brown spending, like investment in new coal plants, investment in new oil fields, and so on. So we think that probably the recovery from COVID was really a missed opportunity, because if you already spent that much money, this would have been a great opportunity to also tackle climate change and not just the economic crisis that COVID brought. Then the second project is about emissions forecasting. So forecasts in general, but also emissions forecasts, are very important for policymakers because they serve as a guidance on how to choose policies, but also for us as a society. They serve as a benchmark to see whether we are on the right track to achieving net zero. But the issue with emission forecasts is that many of them are actually very, very long term. So forecast horizons of 2050 and beyond. So this is just not the horizon that policymakers think in usually. And the second issue is that many of these forecasts are derived from black box models. So maybe we have some description of which variables go into this model, but we certainly don't know the details, and then some company spits out some forecasts, but we really don't know how they came about. And thirdly, many of the forecasts are rather, scenario projections where you make very broad assumptions on population growth, economic growth, and so on, and then come up with some numbers. So the idea here was to build an empirical macroeconometric model. So an empirical model that's actually estimated on data, and where we built a detailed module for the energy sector and the associated emissions, not only from energy, but also other sectors, and then combine it with a macroeconomic model. Because as we know, and as we've heard already from Jenny, emissions are largely driven by economic activity. So your emissions forecast should also be based on economic forecasts, and certainly they should be consistent with each other, which at the moment at least is not always the case. And for this modeling, we want to follow the modeling procedures that climate econometrics has been developing in the past years, with a special focus on accounting for outliers and structural breaks in the processes. Once we have our model, we actually want to distribute this as an open source software to other researchers and policymakers, so that they can adapt the model, they can specify different modules, like they can zoom in on certain parts of the energy sector that they're interested in, etc. And at the moment, we're planning to do everything based on Eurostat variables, so that at least within the Eurozone or the European Union, you can get you can just adapt the model and port it over. So we really hope that we can come up with some transparent forecasts of emissions, and we also want to then subject them to forecast evaluation, like how well do we actually do with this model, because that's also something that's often not done in practice. Okay, and the third and final project is about stranded workers and communities. So we're pretty sure that the green transition will create winners and losers, and we already see now that the negative economic impacts are actually quite concentrated among certain communities, certain groups of workers, but also geographically, some regions that just rely heavily on CO2-intensive industries. So it's very important that we ensure just transition. So the first reason, first and foremost, is that we actually care about these negative welfare consequences. If people get laid off, coal workers, etc., we need to offer them some compensation and help them with life. And the second one is that, especially in the future, as climate policies will need to become more and more stringent, we need to ensure wide public support for these climate policies. And that can only be done if there aren't people who are just left behind. And this work will be joined with Ebba Mark, the incoming DPhil student of the Calleva project. And she already has expertise in this area and has written a paper with co-authors where they've analyzed the unemployment effects of coal mine closures in the US. And they've tried to tease out the both temporal but also spatial dynamics of coal mine closures. And so this is one of their many results. And I want you to focus here on this purple. Is this working? Yeah. Here on this purple line. So on the y-axis, you can say the change in the unemployment rate of a county. And then on the x-axis, you basically see kind of the sequence as coal mines close. So here the point where you see the spike, this is the time period where the coal mine actually closes. And as expected, we see a spike in the unemployment rate. But then they've also found that 2 years later, you actually find a negative spike of about the same magnitude. So that kind of offsets and gets you back to the original unemployment rate. So the question is, well, are we all good? And the green transition only creates transitory unemployment shocks. Well, unfortunately, they've done some further digging, and the reason why the unemployment rate drops again is because many workers just exit the labor force. So either they are retiring, getting disability insurance. These are probably the good cases because then they get monetary compensation, but they might just give up and stop trying. So we want to extend their work and really better understand the geographical dimension of these labor force and employment dynamics. Because there's certainly mobility frictions. People might not want to move to different counties and regions where there's work because they would have to leave family behind. And this also matters for retraining. Like if you want to offer retraining for coal workers, for example, you need to actually check what existing industries is there in neighboring and the specific county that you care about. And then finally, we also want to extend this to the green transition more generally, because coal workers aren't the only ones that suffer from the green transition. There's other occupations, but also there's a much more positive story as well, because the green transition will not just destroy jobs, there will also be a lot of job creation. And we want to model the employment dynamics following from the green transition. Thanks.
This is Xiyu, and I'm an econometrician working mostly at the intersection of economics, statistics, and machine learning. Today, I'm going to talk about econometric methods for evaluating climate policies. And here, first, I'm going to tell about the outline of my research. Basically, my research is just to analyze two types of econometric methods, which are commonly applied in both economics and climate science. The first area of my research is to analyze a model selection, particularly in high-dimensional setup, where we can imagine for big data, where we do have a lot of climate and economic variables. And then we are interested in conducting robust inference, so-called, on the treatment policy variables after model selection. And my second area is to analyze robust estimation and inferential procedures, which is robust to outliers more specifically. And as an econometrician, so the main aim of my research is basically to support empirical climate scientists and economists. And I hope I'm the one who can always be, or the one who can always be found to suggest some econometric methods for the climate scientists and the economist. And furthermore, I think my research is to justify and improve some existing methods popular applied in economic literature and as well as climate science. And because when we step into the climate science with econometric methodology, we can always face some new types of data. That's why it's also important to propose some new econometric methods to deal with the new type of climate type data. And finally, in order to convince the public that our methods is reasonable to use, we always need to develop some econometric theory behind the methods. And so the second aim of my research is basically to build a climate and economic model, which are robust both to specification search and outlier removal. So today's talk is mainly focused on outlier removal, estimation, and inferential procedures. So outlier is a serious problem, either in climate science or economics. So for example, when we do the policy analysis in the so-called, we always use the so-called the difference in difference model, which is kind of popular causal inference to evaluate climate policies. If we do have outliers either in control or treatment group, then our policy analysis is highly likely to be unreliable. And I think thanks to Jenny and Jonas, they both mentioned it's super important to deal with outliers, but they haven't mentioned the methods we have been using. The methods is so-called impulse indicator saturation. It has been it was proposed and analyzed by Jenny, Jonas, and David Hendry. And so basically, the methods we have been analyzing and researching is so powerful to deal with outliers, and it's also it's very general in the sense it can be applied to a general class of the models. So basically, we can take any model of our choice, and we can estimate the model using our outlier robust methods, impulse indicator saturation. So, and there are so many climate or economic applications which needs to apply our outlier robustness methods. As a first example, the first project I mentioned here is a climate policy evaluation. So, for the climate policy evaluation, to be more specific, we focus on whether carbon tax could actually reduce CO2 emissions. And if so, we would like to further evaluate the effectiveness of the policy. And as I briefly mentioned, it relies on the causal inference tools such as difference in difference and synthetic control. And our second project, I think our next speaker, Menghan, will be talking about our second project. It's basically to estimate the climate damage function. It is to explore how temperature or how climate variables, which for example, how temperature and the precipitation could affect economic growth, and it mostly rely on the panel data methods. And finally, we are also interested in estimating so-called environmental coolness curve. And it is basically the relationship between the GDP and the CO2 emissions. For example, with increasing GDP level, we will expect the CO2 emissions would increase, but up to a certain level of the GDP level, further increasing the GDP level, we will expect the CO2 emissions start decreasing. So empirically, we would like to verify whether it is an inverted U-shape. And econometrically, in time series, because both CO2 emissions and GDP are I1 process. So it relies on the nonlinear co-integration technicals. So today I will just focus on our first project, which we would like to evaluate whether carbon taxes can actually reduce CO2 emissions. So carbon taxes is held as a main policy to address climate change. And here there are around 40 very famous economists who support the carbon tax in North America. And so a carbon tax offers the most cost-effective lever to reduce the carbon emissions at the scale and speed that is necessary. But whether empirically we can find empirical evidence to support carbon tax is not 100% clear. So our project is just to evaluate whether a carbon tax is effective enough to lower CO2 emissions. The first carbon tax which was introduced is in British Columbia, Canada, in North America. So here I just plot the CO2 emissions in Canada for 7 provinces. I think the red line is the CO2 emissions in British Columbia, and the 6 green lines are CO2 emissions for six other provinces in Canada. So, and the British carbon tax was introduced in 2008, and so for the red line, it's kind of the treatment group. After 2008, we have the treatment type carbon tax, And the control group is 6 other provinces, so we take average of 6 other provinces at the blue line. Then our aim is really to compare between treatment land, British Columbia CO2 emissions, and the average of the CO2 emissions of the average of 6 other provinces. So we can observe here, before carbon tax was introduced and after, when there is slightly different compare between CO2 emissions, compared between British Columbia and the other provinces. And here we just build up a formal econometric model to formally evaluate whether tax is effective in impacting CO2 emissions. So we also control 2 other variables, population and GDP. We want to say whether beta coefficients here is negative and significant or not. Then first, we just run the very simple ORS panel fixed effects model, which is consistent in our context. So we can get the estimates on tax is minus 0.16, and the standard error is 0.04, so it's negative and it's significant. So from first model, we can find the tax can indeed reduce CO2 emissions statistically significantly. However, once we run the outlier robust methods, impulse indicator saturation, then we can find number 8 outliers, and here we just focus on the tax coefficients. We can say the tax coefficients become much lower, and become much lower, and it only becomes marginally statistically significant. And and there are 2 questions in our mind. The first question is whether outliers detected are truly outliers. The second question is are the coefficients are really distorted by the outliers. So in order to answer the 2 questions, we really need to develop econometric theory. And the simple answer is yes. So the outliers we detected are truly outliers, and in a sense, we really need to rely on the robust impulse indicators, the saturation estimates, to draw the inference. And the first plot, we just plot the outliers detected at the yellow lines, and all the outliers are detected in the SK province. And in the second plot, we just compare 2 estimates. The first, the beta estimates, the tax impact estimates. The blue bar is just the estimates not controlling for outliers. The red bar is the estimates controlling for outliers. We can say there are huge difference between 2 estimates. And from our theory, it highly recommended we draw inference based on the robust estimates. And finally, based on the robust estimates, we found the tax impact on CO2 emissions becomes much lower compared to the OS estimates. That's all about my research. I think my colleague will talk about climate change modeling and prediction.
So I'm going to talk about my research. It's mostly about 2 pillars. First, I'm going to talk about 2 projects about climate change modeling, and then 1 project about its economic impact. So this figure shows the temperature evolution for the last century. The black series is the historical temperature trend, which is exactly the same as what Jenny has shown before. So, but here we are interested in knowing the driving forces of the temperature trends. That's what these 3 colorful lines stand for. We have anthropogenic factors, which is the red and blue line. The red line is for greenhouse gases emissions. This drives temperature up, and we have aerosol emissions that drive temperature down. And we also have natural forcing, that is incoming solar radiation from the top of the atmosphere and volcanic eruptions. We see it basically fluctuates around 0. That means it has little effects on the long-term trends of temperature. So there is one relationship which is of particular interest to climate scientists and economists. That is the relationship between temperature change and greenhouse gases emission. So we have one quantity, TCR, that is a transient climate response. It measures the change of global average temperature given a doubling of CO2. Conventionally, from the climate world, they use global climate models to simulate physical processes happening in the atmosphere, and they gave the TCR based on this. But there is large uncertainty. From the 22 climate models we have in our study, they report TCR ranging from 1.5 to 3. So what we did is we built an econometric model and estimate TCR based on observational data. So we estimate a central TCR at 2.3. with an uncertainty band of plus minus 0.4 degrees, which lies at the upper end of what's given by the climate models. That means we need to revise downward our remaining carbon budget given a certain warming target. Another project I want to talk about is machine learning application in spatial interpolation. It is very common that climate observational data set has limited spatial coverage because they collect the data from observational stations, which is usually concentrated in like developed countries or heavily populated areas. Taking surface solar radiation as an example, we see most observational stations are concentrated in Europe and North America, but there is few stations in South America and Central Asia. So we try to use machine learning method using a range of climate variables, geographical variables, and time indicators to predict values for locations with no observational stations. So this is the output of our model. We have a graded data set with complete spatial coverage. So we report the decadal trends of surface solar radiation over the global brightening period. So we see Europe, Russia, Australia, they are experiencing the brightening period, but for example, India, Middle East, and Southeast Asian countries, they are still experiencing the dimming period. The last topic, the last project is about climate change impacts on economic. I'm going to show first the temperature level and the trends over the past 6 decades. Panel A shows the average temperature. We see high latitude countries in the northern hemisphere are colder and tropical countries are warmer. Panel B shows the decadal trends. The coldest countries experience the largest warming, and all countries have experienced different degrees of warming. So this is for precipitation. Panel A shows the average precipitation level. We see the driest countries are located in Middle East, North Africa, Russia, Mongolia. Wettest regions are located in Southeast Asia, South America. Panel B shows the decadal trends. Countries with hatches do not report significant precipitation trends. Only 17 countries in total report significant trends. Most of them report significant wetting trends, such as North America, Northern Europe, Russia, Southeast Asia. Only 4 countries report drying trends. We estimate how economic growth responds to changes in temperature and precipitation. We see this response surface. There are optimal values for temperature and precipitation. Any departure from the optimums will cause economic damage, or if you have deviations from from each country's specific optimal level. So according to the response surface, we estimate the historical impacts from temperature, precipitation separately and combined together. We see the cold countries experience benefit from the warming. Warmest countries experience damage. Precipitation is shown in the middle panel. We see the wetting trends have a divergent effect for countries with abundant precipitation. At the first place, they experience damage, for example, North America and Southeast Asia. But for countries with dry climate, they experience benefit, such as Russia. And combined together, we see the overall effect is mostly driven by temperature. So a few things we would like to look into in the future. We would like to provide projections of economic growth under different climate mitigation policy and climate change pathways. Because we have seen more extreme weather events, so we are interested in investigating its socio-economic impacts and quantify the change of their frequency and intensity. Up until now, we have been looking into aggregate economy, but in the future, we would like to look into production unit level and industry level and regional level. Thank you. I will give the floor to Susana.
Hello, everyone. So I'll be talking about managing climate-driven global financial risks. So due to globalization and digitization, news can spread immediately. So certain shocks can have a global impact, affecting financial markets all over the world, making them move at the same time. So what are these events that trigger these global extreme shocks and shake the world? I'm not going to talk about earthquakes, although they also shake the world. So this is the global volatility map last Monday. And this is a color-coded volatility map where we can see low levels of volatility across almost all countries around the world. Well, nothing really happened on that day, no big news, no big shock, at least with global impact. And this is the same global volatility map in March 2020, during the COVID-19 pandemic, where many events triggered really large, complex shocks affecting the financial, the volatility of financial asset prices around the world. So this is just one example of these complex events that shake our world, right? But they also include wars, elections, the Brexit, terrorist attacks, and of course, climate change. So recently, regulators and financial supervisors, they have recognized climate change as a new source of financial risks. And these risks, they are widely recognized as arising from two sources, let's say, or two types of climate risk drivers. They can arise from physical acute weather events, such as floods and droughts, or from the slowly changing weather patterns that are likely to result in chronic heat waves, for instance, or sea level rise. And then we have transition risks, and these are, in particular, carbon transition risk is associated, the risk associated with reducing carbon emissions to mitigate the effects of anthropogenic climate change. And these arise from policy changes, so carbon taxes, for instance, technological change, and market sentiment. Now, it's important to identify the events that are affecting the volatilities of all these asset prices, because we expect, especially related to transition risk drivers, we expect this to prompt the reassessment of the value of a large range of assets. So to build climate resilience, regulators, financial supervisors, they are more and more interested in identifying climate-related shocks to financial markets and in integrating climate risk management into business practices and financial decision-making. And this is, we hope, with the results I'm going to show you next, to fill both these gaps in the literature. So given the geopolitical or global nature of both the oil and gas industry and the transition itself, we propose a novel approach to model geoclimatic volatility. So this is climate-driven global volatility. So volatility events that trigger all these volatilities to rise at the same time unexpectedly. And we are looking for those, for the shocks that are driven by climate change. And so we can identify these climate-related shocks to financial markets around the world. So this is a sort of two-step approach. In the first step, we measure any kind of global shock that makes asset prices to move drastically at the same time. And we are going to use the global common volatility model for this. And then we project this measure onto climate-related or climate-driven shocks using text-based or newspaper-based proxies of climate change news. And by doing this, we can show empirically that climate news does make oil and gas share prices all over the world to move at the same time in response to rising climate concerns or more stringent climate policies. But not all geoclimatic shocks are alike. As we will see, the magnitude and the sign of the shock differs across climate risk drivers, and it seems that these risks only materialize when the news is negative and when it reaches the global scale. So this is the results we get from the first step. So here we have the oil and gas global common volatility index. So this index measures the magnitude of these shocks that make all these volatilities of oil and gas share prices to move at the same time. And so we can identify the events that trigger these shocks, right? So we have there the COVID-19 pandemic, we have the terrorist attack, the 9/11, we have elections, right? We also have OPEC announcements. Now, in terms of climate-driven events, it's really hard to find them visually. Around here, it's when we had the deep water oil spill, okay, and this was, of course, an oil shock, and at the same time raised concerns about the environmental impact of these companies, right? So this is also a climate-related event. But of course, we need a more formal analysis, okay, in order to find this systematic association between climate-driven event and movements in financial volatilities. So in the second step, we project this measure onto these climate-driven shocks using these text-based proxies of climate change news. So this is just really an example of what the sort of results we get in this work. So here we have the projection of the global common volatility measure onto climate-related shocks from different from different sources, let's say, so by climate risk drivers, right? And what we conclude from this, so if you look to the right-hand side, you will see the most common words by topic. And what we find is that it seems that only the risks from the transition are materializing and so driving this global volatility and disrupting global financial markets. But we don't really see any evidence for physical risks. Chronic risks, no evidence at all, and we find some evidence that acute weather events can translate into higher global volatility, but only indirectly. For instance, just this example, so droughts, we know that climate change is impacting agriculture, right? So, and this goes back to, or spills over to these oil and gas companies because it creates pressure to reduce carbon emissions and all greenhouse gases, really, in order to mitigate the effects of climate change on agriculture. So with these results, we hope in the future to better understand how the implications of these results to risk management, how this is going to impact global financial stability, and so we hope to help design macroprudential policies. We also hope to develop hedging strategies on how investors can reduce their exposure to these global risks, and also to extend this global common volatility model to have not only global factors, but also group factors, because we expect that assets, they may react differently across groups. So we may find different results for brown assets, which are intensive in carbon, compared to other assets that are not so carbon intensive. In terms of science outreach, so you can find, so we publish on a daily basis the estimates of global common volatility using country equity ETFs and different asset classes. So in this case, you have a more updated sample here. The idea now going forward is to have a similar analysis but for geoclimatic volatility. So researchers, academics, practitioners, they have a way of measuring the magnitude of these shocks, and in this case, driven by climate change. The code is available, so people can really either replicate these results or apply these to the data set, the problem that they have at hand. And also, just to finish, with a group of young scientists from all over the world, we wrote the first fabulous fable of Lorabee. So this is a booklet, an illustrated booklet to communicate climate change to children. The first one, titled Mission Carbon Emissions, was launched at COP26 in Glasgow, and with a 500 environmentally friendly copy giveaway. And we hope to continue the series with other stories and other messages. And last but not least, the booklet is freely available for download at Lindau Nobel Laureate meetings. They were our sponsors with the climate econometrics as well. Thank you so much.
Okay, so last slide, we're concluding. Hopefully, you found all the range of research that we're planning to do and are doing of interest. The project, the Calleva project that we're undertaking, what does success look like? Well, hopefully you'll come back in a few years and we can present the outcome of our project. Success to us looks like advances in our understanding of how to successfully achieve net zero through fundamental research, and that we can influence policy. As I've emphasized, it's interdisciplinary, so we hope to undertake a lot of knowledge exchange between climate scientists and social scientists, but hopefully we've convinced you of the importance of this project, and we look forward to presenting the results of the research at future Calleva seminars. And so we can invite any questions. But just before we do, can I just say Susana's bought copies of her book. So if you're interested in looking at it, do come and talk to Susana and have a look at the book, because it's fantastic. So any questions?
Yeah, I think for environmental acoustics curve, we just focus on a particular country. We didn't do globally. And for now, we just analyze UK and US. We haven't gathered the Chinese data. Yeah.
So you're certainly correct that you need to account for imported emissions as well as domestically generated emissions.
Yeah.
Isaac.
So you just said that you need to account for imported emissions as well as domestic ones. So just to confirm, that is saying that the curve you showed is not accounting for imported.
Sorry, which curve?
Where you plotted the fact that UK carbon
UK
emissions
CO2
per capita
emissions.
have fallen over time.
I'm with you. So I'm trying to remember the data set. Right. Oh, this is a long way back. I'm trying to remember the data set. Here, this one. You're talking about?
Yeah.
These aren't including imports. Of course, imports have changed dramatically over this long time period. So these are domestic CO2 emissions for the UK. So you're right, if you were interested in, you should be interested in the total emissions, including imports, and I think we've got that data, but maybe not to 1860. We should look at that.
Do you know roughly how much of a difference that makes to the overall shape of it? Because that looks very positive, but I don't know how much of an effect is just being sort of hidden by the lack of import data.
So, no, I don't think it would change it dramatically. I mean, certainly we do import a lot, and of course, as the composition of imports have changed towards countries that emit a large proportion of CO2 emissions, this wouldn't look quite so attractive, but I don't think it would change the results very much.
Would it change at the end? Because we've been importing a lot more manufactured products than we used to before.
That's true, yes. So, so there'll be a lot more difference towards the end than the early part of the sample. And as you say, I'm not sure we'd have data on the early part of the sample. I'll have to look at that. So towards the end, but of course that's a dynamic situation as well, because as the countries that we import from start to move towards a green transition, then that will also adjust as well. So yeah, that would be a dynamic question.
Sure. We saw a map of the world with the global volatility. I think it was the second image in during the pandemic. We saw a lot of for example, the Central Africa region was greyed out. Is that greying because we're missing data? Like, how much is that a problem? Because these are the nations, are being affected the most and disproportionately. Is there any scope to kind of try and look for this data?
So that global volatility map is not provable in the data. And the map
This one, yeah.
So this is the example you find on VLab, this website where you can find all these sorts of volatility analysis. And you are right that we don't have data for those African countries. I think because financial markets there are not well developed. In any case, in the example I showed you, so in this paper we use major oil and gas companies around the world. So it doesn't matter where they are based, they are all traded on the New York Stock Exchange. And so the results we find here are unrelated to the map you see because we are using another data set.
Thank you.
So a couple of very sort of non-expert questions from a generalist. So when the UK government was announcing their Green Deal approach recently, one of the things they put a big emphasis on was carbon capture. One thing I wondered was how, in terms of forecasting and sort of thinking about the impacts of policies, how nimble do you have to be, or how possible is it, because, a government could dream up some wonderful new idea, and our government believes that carbon capture is going to be a really positive have a really positive impact on climate change. So how easy is it to build in, a policy change that they might have into your forecasting and modelling?
I think you've hit the nail on the head. The most unpredictable aspect about all of this is government policy, particularly in the UK. So that's extremely difficult to forecast, no doubt. And I don't have a good answer to that. The difficulty with things like carbon capture and storage is, of course, you don't have any time series data as to how successful it is. So it's literally an untested technology. So, I mean, the best you can do is come up with various scenarios about how successful it would be, but in terms of actually using numbers to say this policy will have this effect, the uncertainty bands are just going to be huge.
Sure.
But
As a follow-up sort of related question, which is that one of the things that I think struck many people in the wake of the fuel cost crisis during last year was people suddenly realising that the way our energy is charged is directly pegged to the cost of oil, gas. And many people were pointing out, including the Prime Minister of the United Kingdom, that actually it would be possibly better to go by an average cost, for example. But that is, of course, an economic choice. How you decide to price electricity is an economic choice. So there's an irony here in the sense that there's actual aspects of our economics which themselves, economic choices, could be improving potential outcomes in terms of the climate, because it could be driving, economics could be driving itself choices which were moving towards a greener approach to energy provision. So I guess that's a sort of double reason to use this kind of approach in a way, because economists can inform other economists about what actually would be better in terms of how we do things, I guess.
yeah, no, said perfectly. I completely agree, yes. I mean, the irony, of course, is that renewable energy, cost of it is just falling absolutely dramatically, and yet the electricity prices are pegged to fossil fuels, so madness.
We've had a question come through about carbon taxes. Carbon credits/offsets developed in response to the Kyoto Protocol were criticized as inefficient to address the scale of emission reduction. Is this considered when modeling carbon taxes?
Okay, do you want to answer the carbon taxes question?
I don't know if it was addressing the diff and diff modeling in particular, but I guess maybe the question is, like, if we do identify a robust effect, is it enough? Maybe.
Yeah, I think our main aim to still evaluate carbon taxes is just to, I mean, what we are trying to emphasize is whenever we draw some conclusion based on the policy analysis, it's always better to be based on the more robust estimates, either robust to different models and also robust to the outliers. And we are not trying to say our estimates is the best estimates to conclude the carbon tax policy analysis, but we are just trying to go one step further compared to the OS estimates. I think, yeah.
No more questions? Everyone's ready to get away for dinner. Thank you.
In which case I'll just thank Jenny and her team very much indeed for the presentation today. It's really appreciated. Thank you. And it's going to be great to see how the work progresses over the next couple of years and beyond. So thank you. And there are some refreshments outside if you'd like to stay to talk to Jenny and her team more informally afterwards. Thanks again.